Hey everybody, we're going to do systems of equations today. Today we're going to solve them by graphing. Your EQ today, how can I use graphing to solve a system of equations, and how can I tell if the answer I get really is the solution to that system? So to start with, a system of equations is two or more equations comprised of two or more related variables. That's just the definition of what a system is. So system of equations. Got two examples down here. One is a system and one is not a system. Again, it's all about the variables being related. This first one over here to the left is a system because you'll notice there's two equations and they both have the same two variables inside. They have the x and the y in both of them. This one over here on the right is not considered a system because even though there's two equations with two variables in each one, the variables aren't related. The x and the y might be different than this x and the z down here. So the one on the left is a good example of what a system looks like. It could be a three equations in your system. You would just want to make sure you had three related variables in each equation, and so on. Forgive the rough cut on this today, guys. Since I'm kind of late getting it up, I'm not going to do a lot of editing, so you have to forgive all my ums and goofs on this one. So here we go. The solution for a system of equations is the point where the two lines cross, where they intersect. So if you have two really pretty equations, like in example 1 here, you can quickly graph them and see where the answer is. This doesn't work for all systems of equations. Sometimes they're uglier and messier, and that would take a different method for solving it, but that's going to be the next unit. So let's start off with this very first one right here. If you have two different colors to graph in your notes, that would be really great. If not, pause this right now and go grab a colored pencil or a marker or something so you have two different colors to graph in. It really makes systems a lot easier to see. I'm going to start by graphing this first equation right here in red. Remember, y equals mx plus b, so I graph my y-intercept, and then my slope is up 1 over 1. Up 1 over 1. Okay, forgive the time-consuming nature of this plotting. Normally we just plot a couple of points and get on with life, but the thing with graphing to solve a system is that you want to be really, really accurate, because the point where the two lines cross is the answer. So you guys know that I can't draw a straight line to save my life, so I think my red dots represent my line pretty well, so I'm just going to leave my line just as is. If I try to draw the line, it'll be harder to see my answer. I'm going to graph this second line in a different color. So with the y-intercept of 10, and then my slope is down 1 over 1. So watch what happens as I keep going down 1 over 1, right there. Notice how I just drew a blue dot right on top of the red one from the previous line. That, my friends, is the answer. That's the solution. So right down here, where it asked me for the solution, I would write that ordered pair. So over 7 up 3, it looks like. So 7 comma 3 is the solution to that system. So you're thinking, well, what the heck does that mean? Well, basically what it means is that's the point where the red and the blue line are both exactly the same. That's where they cross. They both exist at the same moment in time right there at that point. You could also look at it this way. 7 comma 3, that's just an x and a y. So that means that I could take those x's and y's and plug them back into my equations up top, and if they work, then I know it's a solution. The key is that they have to work for both equations. If it works for one and not the other, then something's wrong. You need to double check. So that's what we're going to do right here. Check with substitution. I'm going to substitute my x and y, the 7 and 3, back into the original equations. Here's what I mean. If this is x and this is y, my first equation is y equals x minus 4. So I would write 3 equals 7 minus 4, because 3 and 7 are my y and my x. When I do the work, 7 minus 4 is 3. So bring the 3 down, bring down the equals, do the math, and I'm left with 3 equals 3. That's a true statement, so it worked for the first one. Now let's check the blue one. Same deal, I'm going to use the same numbers, 7 and 3, and plug them in. So 3 equals negative 7 plus 10. Bring down your 3, bring down the equals, and now we're going to do the math. Negative 7 plus 10 is 3. That's also a true statement. Since I get a true statement for both situations, that means that my solution over here is good. 7, 3 really is the answer. Another way you can check your work is by using your calculator. That's what this table up here is all about. If we go to our calculator and plug in those equations, then we can go to the table and see if that point exists, if that's the point where they're both the same. So bear with me while I put this in my calculator. If you have your calculator, I would recommend doing this along with me. So on my calculator, I'm going to go to y equals and type in the first equation, x minus 4. And then down for my second equation, negative x plus 10. And I could hit the graph button, and hopefully it looks like the graph approximately that I just graphed on my by hand, I guess. And then I could go to the table. That's actually what I want to look at. Okay, remember y1 is the first line, the red one, and y2 would be the blue one. And now I just want to scroll to my point, 7, 3, and see what there is to see. Oh, look right there. 7, 3 on the first line is the same as 7, 3 on the second line. By verifying that that point exists for both lines at the same time, that's how I know my answer's correct. So once upon a time, we used our table to check our answers. Remember, we put the answer right in the middle, 7, 3, 3. And then we did one line above and one line below just to prove to Miss Potts that you actually did the checking. So 6, 2, 4. And the bottom one would be 8, 4, 2. We'll go over this again in class if the table is throwing you just a little bit here. Again, it's just a way to check your answer, check your graphing to see if you did it correctly. And this is the part that's important. That's what tells you that you did it correctly. Let's try another one. Here we have another one that's set up in y equals mx plus b form, so hopefully it will be nice and easy to graph. I'll start by graphing in blue. My y-intercept's at negative 3, and my slope is up 1 over 2. Graph that second one in red. Negative 6 halves. That looks like kind of a goofy y-intercept, but I know that negative 6 halves is the same as negative 3, because 6 divided by 2 is 3, right? So there's my y-intercept, and I just happened to graph it right on top of the blue line. Very interesting. So that looks like that's probably my answer. Before you just stop and write that down, though, I'm going to caution you against that. Go ahead and plot a few more points, because watch what's about to happen. Up 2 over 4 is my slope. So up 2 over 1, 2, 3, 4. Look what just happened again. And if I go up 2 and over 4 again, notice what's happening here. If I go backwards and go down to left 4, down to left 4, notice that I'm plotting the same points over and over and over again. What this is telling me is that there's not just one single solution. I've clearly found a bunch. If you come back up and look at our equations, you'll probably notice that there's something pretty special about them. What does 2/4 simplify down to? Well, it's 1/2 x, and we already know that 6 halves simplified down to the 3. Notice that this equation, the second equation, is exactly the same as the first. That means when I graph the blue line and then when I graph the red line, I'm just graphing the same line, one right on top of the other. So if you think about it, well, how many times do those two lines touch? How many times do they intersect if they are graphed one right on top of the other? Well, I already see 1, 2, 3, 4, 5 places. And I have a feeling that they probably touch a whole lot more. Because if I graphed my slope up 1 over 2, they'd touch there and there and there as well. Since they're the same line, if I actually draw the line, you have to remember that there are infinite points on the line. So they touch an infinite number of times. So the solution here is, we'll just say infinity. All points. You could say all real numbers, perhaps. That would be another good way to look at it. It's every single point, all of these on here. They are all solutions. I could pick any one of them and plug it back in and it would work. So let's go and let's take a look at how this looks in your calculator. If you wanted to check to make sure that really was true, obviously we don't want to plug every single point in by substitution and do it by hand. That would be kind of a pain. My calculator's a real quick way to check this one. So 1/2 x minus 3 and then we had 2/4 x minus 6/3. No, 6/2, sorry. If I graph them, you'll see the first line, and we wait, and it looks like the second line never pops up. What happened? Well, remember, we just graphed the same line on top of each other. So if that happens, don't be alarmed. Go check your table to see if you can figure out what's going on. This time you'll notice that we can't scroll to any one point to see the solution because they're all solutions. Every last one of them. So notice here, 6, 0, 0. And then if I go down to the next one, 7.5.5. You're going to find solutions no matter where you look. Alrighty. I'm going to graph this one real quick. I'll pause this so that you don't have to see the entire process, and then I'll come back to you in just a minute. Okay, check it out. So I just graphed these two lines. And again, my solution is the place where the two lines intersect. So I'm looking at my grid here and I'm thinking, well, I don't see any place where they intersect. So what's going on with that? Well, first I'm going to double check it. They look like they're not exactly the same line. Obviously they have a different y-intercept. This blue one I graphed with a slope of up 2 over 4, up 2 over 4. But remember, that's the same as 1/2. So I could have gone up 1 over 2. If I throw a few more points in there, then it becomes very clear that these lines are parallel. So if you think back to when you very first learned about parallel lines, how many times do parallel lines touch? None. They never touch. That's kind of the definition of parallel lines. So if they never ever intersect, then you can't find an answer. There is not one single point on the face of the planet that you could plug into those two equations and make it work for both of them. So in this case, the solution is an empty set. There is no answer. There is no solution set. Alrighty, last one. I think it's the last one anyway. In this case, same situation. I've got a system. I need to solve it. I've got to figure out what x and y are. It's not going to be quite as easy, unfortunately, because notice they're not in slope-intercept form. So I'm going to take a minute and solve these for y. And then I'll graph it. So there's my first one. I'll quickly solve out the second one and then be right back. Okay, so I solved the second equation for y as well. And I went ahead and graphed the red equation as well while you were waiting on me there. Now I can take a minute and graph the blue one and see if I can find a point where they're going to intersect. Y-intercept of 2, and my slope is down 1 over 1. I'm pretty sure I found my answer right there. Down 1 over 1, down 1 over 1. So it's pretty evident that these are not the exact same line. They are not parallel lines. They're just simply two lines that cross one single time right here at this point. So that's my answer. Remember, your solution is an ordered pair, 1, 1 in this case. To check it with substitution, it just means you plug your x and your y back in. Alrighty, so one more time, I took my x and my y values and I plugged them back into the original equations. And when I checked it in both, I got 6 equals 6 and 6 equals 6. That means it works for both equations, so 1, 1 is my solution. One last one down here. I'm going to go ahead and work it without you having to listen to me so that you can just have one extra example down. And then we'll write questions and summaries together today. Alright, so there we go. I solved them both for y. I plotted them, and then that's the point where they crossed over each other. So my solution this time is 4, 0, it looks like. Again, don't just take your own word for it. Check it with substitution. It's one of those things that's so easy to do if you'll just take the time to do it. Notice what you can do as well. See, notice how I can't see my two original equations. I'll have to scroll back and forth. I'm just going to use these guys because those are my original equations. I just manipulated them. I just turned them around a little bit. So I'm going to just use those instead. This works out because bring down these guys. Negative 4 plus 4 cancel out. So 0 equals 0. Same situation here. 8 minus comes down. 2 times 4 is 8. 8 minus 8 really does equal 0. 0 equals 0 is a true statement. That means 4 comma 0 was a good solution. So the last thing we need to do is to write our questions and write our summaries. So let's scroll back to the top, right there, and remember that you want to write a question for each chunk of information if possible. I'm going to go through and write them, and then you can just jot them down. And next time we do notes, you can go back to doing them on your own. Okay, everybody, here are the questions and the summary for this set of notes. I'm just going to quickly scroll through them. You can pause as I'm going along so that you can stop and copy them down. I'll see you guys tomorrow.